just about 10 o'clock. So how did everybody feel about the midterm? Reasonably comfortable?
I think I did okay. There was just
Awesome.
like one thing I wasn't so sure on, so that's okay.
There's always things that I'm not sure about also. Okay, well.
But you're a professor. You're an expert. Doctor in
Yeah,
you.
that's what we tell you. Okay, so today I want to talk about determinants. This is basically chapter 3. So a determinant is a function that you can plug a square matrix in and it gives you a number. So a determinant from n by n matrices to the real numbers. We're doing everything over the real numbers. That has particular properties, which we'll talk about in a little while. Well, let me show you how to compute it. So let's start off with 2 by 2 matrices. It's very easy to compute the determinant of a 2 by 2 matrix. So given a 2 by 2 matrix, A, which we'll write its entries as A, B, C, D, like that. The upper left-hand corner is little a, the upper right-hand corner is little b, and so on. The determinant of A so I could write this as the determinant of A, I could write it like that. I could write the determinant of A, B, C, D, since that's the same as A. Another notation that you sometimes see is the same matrix, the same entries, A, B, C, D, except instead of writing the brackets around them the way we usually write matrices, you just put bars around them. That says take the determinant of this matrix. This is an older notation, but it's still in use. To take the determinant of a 2 by 2 matrix, all you do is you take the upper left-hand corner times the lower right, A times D minus B times C, minus the product of the ones off the diagonal. That's all there is to it. Taking the determinant of a 2 by 2 matrix is a piece of cake. So let me just give you an example. Find the determinant of, let's say 1, 2, 3, 4. Excuse me.
Bless you.
Thank you. So according to the rule that I gave you down here, the pattern, you just take 1 times 4 and subtract off 2 times 3. And what do you get?
-2.
Exactly, you get -2. Is there anybody who's not completely confident in their ability to be able to take the determinant of a 2 by 2 matrix? Okay, I didn't think so. I just want to make sure before we go on. Now, to take the derivative of larger matrices, we use what's called, or we can use what's called cofactor expansion. Larger square matrices. We can use something called cofactor expansion. This word right here is cofactor. Just factor with co in front of it. Now, let me explain what I mean. So let's go to 3 by 3 matrices. So let's write a 3 by 3 matrix. Just the letters down. So A, B, C, D, E, F, G, H, I guess I. Now, when you're doing a cofactor expansion, you can do a cofactor expansion across any row that you want or down any column. So we can do a cofactor expansion across any row or down any column. So I'm going to choose to do a cofactor expansion this time down the first column. So this is my choice. You'll get the same answer no matter how you do it. The first column is just ADG. And for a particular matrix, you can choose whichever one makes it easiest for you. Sometimes going across the second second row is the easiest thing. Sometimes going down the third column is the easiest thing. It just depends where the zeros are. Now, the cofactor, so we have like 3 entries in the first column. The cofactor of A, or cofactor of A, little a. So A is up here in the first row, first column. What you do is you cover up the first row, cover up the first column, and you're left with this 2 by 2 matrix down here. So the cofactor of A, if we cover up the row that A is in and cover up the column that A is in, we have this 2 by 2 matrix EFHI. The The cofactor of D, so we said we're going down the first column. The cofactor of D is cover up the row that D is in, cover up the column that D is in, and you have a 2 by 2 matrix. Go ahead and write it down. Cover up the row that D is in and the column that D is in, and you see 4 entries. So you should see B, C, H, I. And there's one more entry in the first column, and that's G. My G looks like a Y. I don't know why. So the cofactor of G is cover up the row and the column that G is in. Oops. And you should see B, C, E, F. Is everybody okay with this cofactor business yet? I haven't told you what to do with the cofactors, but can you just write them down? Is that okay? Awesome. Okay. Now the other thing that you need to be able to take the derivative of a 3 by 3 matrix is the following checkerboard pattern. You just start in the upper left-hand corner with a plus sign, and then just alternate, like minus, plus, and then, minus, plus, minus, plus, minus, plus. It's like the checkerboard pattern with the black and the white squares. Or or what is it? On checkerboard, I guess it's red and black. And on a chessboard, it's black and white. Whatever. You get the idea. It's just a checkerboard pattern. And in the upper left-hand corner, there's a plus sign. Okay, so here's what we do with the first column, since we decided to go down the first column, and these cofactors. The determinant of A, determinant of this 3 by 3 matrix, if we're going down the first column, is, now follow these plus and minus signs. We were going down the first column. So the determinant of A is plus little a times the determinant of its cofactor. So the cofactor of A is EFHI. Minus the next entry in that column, which is D, times the determinant of its cofactor, BCHI. Plus the last thing in that column, G, times the determinant of its cofactor, which was BCEF. And you already know how to take the determinant of a 2 by 2 matrix. So you know that this is equal to A times the determinant of this matrix is EI minus FH. Minus D times the determinant of this matrix is this times this minus this times this. BI minus CH. And plus the determinant of this matrix is G times BF minus CE. And I suppose we could write that a little bit more simply. AEI minus AFH minus DBI, a plus, minus times minus is plus, DCH plus GBF minus GCE. So to take the determinant of a 3 by 3 matrix, you have to take 3 determinants of a 2 by 2 and string them together like this. Is everybody okay so far? Awesome. Now, is there anything you notice about each of these products? So you can see there's 1, 2, 3, 4, 5, 6 products that you have to compute when you take the determinant of a 3 by 3 matrix. Is there anything you notice that's true about each of the products? If you think about where these things are in the matrix, like let's take a look at the first one, A and E and I. So A and E and I are like this. And then the next one is A and F and H. And the next one, it's getting messy. The next one is D and B and I, and so on. Is there anything you notice about each one of those products? Requires a good deal of insight to see it. Well, let me just tell you. Notice, let's look at the third one, D and B and I. So this and this and this. Notice in D, B, and I, exactly one of those letters is in each row. D is in the second row, B is in the first row, and I is in the third row. And notice that exactly one of those is in each column. D is in the first column, B is in the second column, and I is in the third column. All of these are like that. In each one of these, you have exactly one letter in each row and exactly one letter in each column. You never have like 2 in one row and 1 in another row. That never happens. And in fact, these are all the products where exactly one thing is in each row and exactly one thing is in each column. There is exactly 6 of them. They're all there. Now, I said we could go down we could go down any row or across, go down any column or across any row we wanted. I want to go ahead and compute exactly the same determinant, except this time, instead of going down the first row, let's go across instead of going down the first column, let's go across the second row. I just picked that arbitrarily. I want you to see that you get exactly the same thing. So we could, instead of doing this down the first row, we could also go, down the first column, we could also go across the second row. So the determinant of A is, let's go across the second row. So it's going to be D times the determinant of its cofactor. So cross out the row and the column with D in it, and you see BCHI. Oh, sorry, that should be minus because there's a minus sign in front of that. So there should be a minus in front of that D. So minus plus E, and write down its cofactor, determinant of, let's see, We cross out that column and that row. I see ACGI minus F times the determinant of its cofactor. If I cross out the column and the row with F in it, I see ABGH. And if I work this out, I get minus D times BI minus CH plus E times AI minus CG minus F times AH minus BG. And so I have here minus dBi, minus times minus is plus dCH plus EAI minus ECG minus FAH plus FBG. Once you work it all out. Now, I said you'd get the same answer no matter how we did this, so that had better be the same as what we have over here. Let's see. So minus dBi, there it is. Plus dCH, there it is. Plus EAI. Okay, I wrote it as AEI over here, but EAI, AEI, they're the same. So there it is. Where were we? Minus ECG. Minus ECG. I wrote it in a different order, but the order in which you multiply things doesn't matter. There it is. Minus FAH. AFH, that's the same letters, multiplied in different order. There it is. And plus FBG. FBG. There it is. It's exactly the same. It gives you exactly the same number. Does that seem okay? So let me ask you to compute. Well, before we go on, does everybody get it so far? Let me ask you to compute the determinant of this matrix. How about 3, 5, 2, 0, 1, 2, 0, 3, 4. Do it by cofactor expansion. Pick a row, pick a column. Pick a row or pick a column, and do it by cofactor expansion. So if it were me doing this, I'd pick the first row because there's a lot of zeros in the first row. And multiplying by 0 is easy. So I would go down the first row. I would say that this is equal to plus, we're using that checkerboard pattern that we have over there, plus 3 times the determinant of its cofactor, 1, 2, 3, 4, minus 0 times the determinant of its cofactor, but who really cares? But I'll just write it down. 5, 2, 3, 4, plus 0, so times the determinant of its cofactor, 5, 2, 1, 2. I don't even have to compute these two because there's just zeros in front of them. So this is just going to be 3 times the determinant of this, 1 times 4, minus 2 times 3, minus 0 plus 0. And so this is equal to 3 times 1 times 4 minus 2 times 3, 3 times negative 2, which is negative 6. You could have easily gone across a row or gone down a different column, and you should still get negative 6. Is everybody okay with that? So this determinant function ate this 3 by 3 matrix and gave us back a number. Now, let's go on to 4 by 4 matrices. We're still going to do this by cofactor expansion. Actually, I'm going to need more Blackboard space, so let me wait till you're finished writing everything down. You got everything? Okay, I'm going to erase. I guess the nice thing about this is you can always back up. Good, I'm recording. Later, if you watch this again. So we use the fact that we were able to compute the determinant of a 2 by 2 to compute the determinant of a 3 by 3. So let's move to 4 by 4. So the determinant of, let's say, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I hate using O as a variable because it looks a lot like a 0, but whatever. Again, you can do a cofactor expansion down a column or across a row. Any one you want, and you're still going to use that same checkerboard pattern with the pluses and the minuses. Plus, minus, plus, minus. We always start with plus in the upper left-hand corner. Minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Let's say I want to go down the first column. You could go across any row or down any column you want. I'll go down the first column. Then the determinant of this matrix is equal to A times the determinant of its cofactor. Cross out the column and the row that A are in, and you're left with this 3 by 3. F, G, H, J, K, L, N, O, P. So there's a plus in front of the A from the checkerboard pattern. You write down the A that's in that position, and then you write down the determinant of its cofactor. So if we're going down the column, the next thing is E. It has a minus sign in front of it. Minus E times the determinant of its cofactor. Cross out the row and the column that E are in, and you end up with BCD, JKL, NOP. Plus, now the determinant of its now plus I, and the determinant of its cofactor. So that's BCD, FGH, NOP. Minus M times the determinant of its cofactor. BCD, FGH, JKL. So we've turned the determinant of this one 4x4 matrix into 4 determinants of the 3x3 matrices. And you already know how to compute the determinants of the 3x3 matrix, right? You know how to take the determinant of this, and you know how to take the determinant of this, and you know how to take the determinant of this, and you know how to take the determinant of this. You just showed me you could do it. We just did a problem where you took the determinant of a 3x3 matrix. Each of these 3x3 matrices you take the determinant of by taking the determinant of 3 2x2s. So when you take the determinant of a 3x3 matrix, how many terms were in our answer? When you count up the number of terms that when we just took the derivative of the 3x3, how many terms were there?
3.
How many?
6.
6. There were 6 altogether. So there were 6 terms here. There's going to be 6 terms. There's going to be 6 terms here. 6 terms. 6 terms. Add them all up, you get 24 terms. So for a 2x2 matrix, there were 2 terms, right? AD times minus BC, 2 terms. For a 3x3 matrix, there are 6 terms. For a 4x4, there are 24 terms. Does anybody recognize these numbers, 2, 6, 24? For a 1x1 matrix, the determinant is just A. So for a 1x1 matrix, the determinant, there's just one term. It's just the entry itself.
It's a factorial,
Anybody
right?
recognize these numbers? 1, 2, 6, 24?
That's factorial, right?
Yes, it's factorial. 1 factorial is just 1. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. And 4 factorial is 4 times 3 times 2 times 1, or 24. Has everybody seen factorial before? Okay, good. Good. How many terms are there for a 5x5 matrix?
What is it, 120?
120, yeah. 5 factorial will be 5 times 4 times 3 times 2 times 1. In other words, you're just going to take 5 and multiply it by the previous number, 24. 5 times 24 is 120. So there are 120 terms. For a 6 by 6 matrix, it'll be 6 factorial, 720 terms. Anybody want to compute the determinant of a 6 by 6 matrix using cofactor expansion? No, me neither. I've never done it, never want to do it. No. So the most I think I'd be willing to do via cofactor expansion really is a 3 by 3. I'm not even thrilled about the idea of doing a 4 by 4. So there has to be an easier way to be able to compute determinants when we need them for these larger matrices. And there is. What we need to do is understand the properties of determinants to be able to do that. But so far, does everybody get what we're doing so far? Awesome. Okay, let me just bring this over. And really, in a pinch, if you had to, you could compute the determinant of a 4 by 4 matrix or a 5 by 5 matrix or a 6 by 6 matrix using cofactor expansion. If I said, if somebody ever says, you're in jail and you're going to stay there until you've computed the determinant of this 5 by 5 matrix with cofactor expansion, you'll be out before lunch, assuming you don't make any mistakes. Okay, so let's talk about properties of determinants. Let's first talk about triangular matrices. So a triangular matrix is a square matrix which is either all zeros below the diagonal, so this is called an upper triangular matrix. Or it's all zeros above the diagonal. And this we call a lower triangular matrix. I'll give you an example. Let's say I give you an upper triangular matrix. How about 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 8, 9, 0, 0, 0, 10. So this is an upper triangular matrix. Below the diagonal, it's all zeros. So the diagonal is 1, 5, 8, 10. all zeros below the diagonal. If I had an upper triangular matrix, it would be all zeros above the diagonal. Everything above the diagonal would be 0. Is everybody okay with this so far? Let's go ahead and compute the determinant of this thing. Now, it's a 4 by 4. You'd think we would have 24 terms. But let's go down the first column, because there's a lot of zeros there. So the determinant, let's call this A. The determinant of A is equal to 1. So we're using that plus, minus, that checkerboard pattern, times the determinant of its cofactor. So 1 times the determinant of its cofactor. If I cross out the row and the column with a 1 in it, I end up with 5, 6, 7, 0, 8, 9, 0, 0, 10. Minus 0 times, really, who cares? Determinant of its cofactor, but I'm not going to write that down because it's going to be 0 times it, which is 0, plus 0 minus 0. So a whole lot of zeros. So most of the computation just went away. So it's 1 times, now let's take the determinant of this matrix. I'm going to go down the first column again because there's a lot of zeros. I'll go down the first column again because there's a lot of zeros. So the determinant of this matrix is 5 times the determinant of its cofactor. Minus 0 times the determinant of its cofactor, but I'm not even going to write that down, plus 0 times the determinant of its cofactor. I'm not going to write that down. So we have that 1 and that 5. Now let's take the determinant of this 2 by 2. 8 times 10 minus 9 times 0. What do you notice about the determinant of this original matrix A, which is 1 times 5 times 8 times 10?
The diagonal.
Yeah, it's just the product of the diagonal entries. So note, determinant of A is just the product of the diagonal entries. And that's true of any triangular matrix. For exactly the same reason. We could just keep going down. If it's an upper triangular matrix, we could just keep going down the first column every single time. Or if it's a lower triangular matrix, we can just keep going across the first row every single time. And we're going to end up with most of it disappearing in zeros. So the determinant of any triangular matrix is just the product of the diagonal entries, whether it's upper triangular or lower triangular. Matrices which are both upper triangular or lower triangular are called diagonal matrices, because if everything is 0 below the diagonal and everything is 0 above the diagonal, then the only thing that's not 0 is on diagonal. And so it's true of diagonal matrices also. That's one of the lovely things about triangular matrices. It's super easy to compute the determinants of them. It's not true of a non-diagonal matrix. So without breaking a sweat, what's the determinant of this matrix? What's the determinant of that matrix?
1.
It's 1. 1 times 1 times 1 times 1, 1. Nothing to it. So determinant of triangular matrices, easy. Let's talk about how determinants change when you do a row operation. Now, the proofs of all this stuff are in the textbook. I am not going to make a big deal about the proofs this semester because of our unusual circumstances. But if you are curious, you can find all the development of this stuff in the textbook. Let's see. So remember, when I'm talking about row operations, we have 3 kinds of row operations. You've been doing a bunch of row operations. Doesn't matter how we order them, but one is called replacement. If we replace a row by itself plus a multiple of a different row, that's what replacement's all about. Replacement doesn't change the determinant at all. It doesn't change it. So in other words, if A and B are both square matrices that are identical, except you get B by doing a row replacement for A, if A and B, let me phrase that differently. If matrix B is obtained from matrix A by doing a row replacement, the determinant B equals the determinant of A. Sorry. I did not realize that we had run out of time. I didn't even think we were within 10 minutes of the end. Time flies when you're doing linear algebra. Are there any questions before we head out? Okay. Thank you for your patience, and sorry I went over time. Try to keep a better eye on the time from now on, and I will see some of you in 9 minutes, and I will see others of you on Wednesday.